In this lesson, we'll be investigating the alternate theory of acids and bases. Our lesson objectives: define Bronsted-Lowry acids and bases, compare the Arrhenius theory to the Bronsted-Lowry theory, and define amphiprotic substances. There is an alternate theory of acids and bases and a way of defining them in addition to the Arrhenius theory, and it's called the Bronsted-Lowry theory of acids and bases. And this theory allows us to help classify NH3, which is ammonia, as a base, even though it is lacking the OH, the hydroxide ion, in the chemical formula. And so according to this alternate theory, we define acids as a substance that donates an H plus ion, and bases accept the H plus ion. And we can remember that using the acronym BAD, where bases accept the H plus and acids donate. And so let's see what that looks like. Here's an example between an acid and a base. I'm including the NH3 here, which we now know is defined as a base. And so what happens is that NH3, you see, will form NH4+. So it's getting an H plus from somewhere. In this case, it's getting it from the water. You'll see that water ends up losing the H plus to form an hydroxide ion. So the NH3 accepts the H plus from water. So since it's accepting the H plus, by definition, that is a base. And the water is donating the H plus. And so by donating, that's defined as the acid. And so you can see also why NH3 is considered a base, because look what happens when it does interact with water. It does lead to the formation of hydroxide ions in solution, as we know indicates the presence of a base. And so let's look at the particle models below to help solidify this understanding. Here we have our NH3, our ammonia, and you see it forms the product NH4+, ammonium ion. So it gained an extra H, as you can see here. Where did it gain that H from? It gained the H from water, which lost it to form the hydroxide ion. So by definition, this gained an H, it accepted it, that's my base. The water lost the H+, it donated it, that's my acid. The H+ is often referred to as a proton. So acids are classified as proton donors and bases are proton acceptors. Why is H+ often classified as a proton? Because if we look at the hydrogen atom, it's consisting of one proton in the nucleus and one electron outside the nucleus. But when it forms the H+ ion, it loses that electron. So it is only made up of the one proton. So H+ is synonymous with being a proton. And so sometimes it's referred to as just a proton. So let's check your understanding. Can you define Bronsted-Lowry acids and bases? So what happens when an acid dissolves in water? As we see here, we have hydrochloric acid and we have water. So in this reaction, water is going to act as a Bronsted-Lowry base, and it will remove the H+ proton from the acid. And so therefore it's going to gain the H+, and by definition it becomes a base. And it's going to form the hydronium ion, and we'll get the chloride ion in solution, and we know that charged particles will allow for the conduction of electricity. Let's check your understanding. Can you define Bronsted-Lowry acids and bases? Can you compare Arrhenius and Bronsted-Lowry acids and bases? Lastly, let's look at something called an amphiprotic substance. This is a substance that's able to act as an acid and a base. So it can either donate the H+ or accept that proton, that H+. Some examples are water, HSO4- and HCO3-. These all have the H ion, the hydrogen ion, to be able to donate it and act as an acid, and also a negative charge associated with the substance, and it's able to accept an H+. So you can see here in each of these groups, I show you how it's acting as an acid and as a base. So for example, here's water. Water can accept the H+, and so by definition it would act as a base to form the hydronium ion. And water can also be split apart into H+ and OH-, and so in this case it's losing or donating the H+, and that would act, as you can see here, as our acid. And the same thing for the other groups of substances. HSO4- can either accept the H+, like a base, or it can act as an acid by donating its H+. Let's check your understanding. Can you define amphiprotic substances? And lastly, let's compare acids and bases using the Arrhenius theory and the Bronsted-Lowry theory. So here is HCl. We're going to dissolve in water. We form hydrochloric acid. It's going to dissociate into the H plus and the Cl minus ions. And recall that acids will conduct electricity because we have these charged particles, and that's why they are considered electrolytes. Now, according to the Arrhenius theory, this is classified as an acid because it's producing H plus as the only positive ion in solution. According to the Bronsted-Lowry theory, it's also classified as an acid because it has this ability to donate this H plus. Looking at the base, here's sodium hydroxide. It will also dissociate in water to form positive and negative ions, and it's also classified as an electrolyte. Now, according to the Arrhenius theory, it's classified as a base because it's producing OH minus, the hydroxide ion, as the only negative ion in solution. And it's classified as a Bronsted-Lowry base because it will have the ability to accept the H plus ion. Let's check your understanding. Can you compare Arrhenius and Bronsted-Lowry acids and bases? At this point, you should be able to define Bronsted-Lowry acids and bases, compare Arrhenius and Bronsted-Lowry acids and bases, and define amphiprotic substances.